In the sixth video for chapter 6, so video 6-6, we're going to be looking at writing formulas for ionic compounds that contain polyatomic ions. So remember, these are ions, so they will undergo ionic bonding to form neutral ionic compounds. When you have a polyatomic ion, remember that it always contains several atoms bonded together for each individual ion. So if you have multiple ions, when you're balancing your ionic structure, you're going to need to use parentheses. What do I mean by this? For example, in this example, we take barium. Barium is a cation. It's got a +2 charge. And if we react barium with nitrate, nitrate is NO3 -1. Oops. NO3 -1. We'll just put a negative there. We see that the charges don't balance out. We have a +2 for the cation and a -1 for the anion. We know that we need a total of +2 and -2 to balance the ionic compound. So you could crisscross if you wanted to. You could bring the integers down, so the 1 and the 2. We typically don't write the 1, so we won't write that. But we're going to bring the 2 down here, okay? And we're going to put the 2 here. Now, there's a problem here. There's already a 3 as a subscript for nitrate. So if I put a 2 beside it, I'm saying there's 32 oxygens in this compound? No. When we write the subscript 2, we indicate that there's 2 nitrates, ions. Nitrate is NO3 -1. So we want to indicate that we have 2 of those. Then we use parentheses around the polyatomic ion. Anytime you have more than one polyatomic ion needed to balance the overall charge in the ionic compound, you're always going to use parentheses. So let's practice. Here's the formula for each cation and anion. So here we have manganese with a +2 charge. And we have carbonate, CO3, -2 with a -2 charge. So when we want to write the correct formula for the ionic compound, remember we're balancing charges. Notice this time we have a +2 and a -2. Those are equal and opposite charges, so we only need one of each ion. The formula will be Mn, manganese, CO3, carbonate, manganese carbonate. Notice I did not use parentheses around the carbonate. Don't do what I'm about to do. But if you wrote parentheses around carbonate, that would be incorrect. The only time you need parentheses around a polyatomic is if you have multiple ions of the polyatomic present in order to balance the compound. Alright, let's look at the next one. The next one is strontium and hydroxide. Strontium is a +2 charge. And our anion is hydroxide, OH -1. So we have a -1 and a +2. We're going to need 2 hydroxides. So when we go to balance the structure, we do not write, or the formula, we do not write OH2. In this formula, it says that we have 2 hydrogens and only 1 oxygen. But remember, hydroxide is a unit, and we need 2 of the entire unit. So when you have multiples of the polyatomics, you're going to use the subscript to balance the charge. Let's see here. I think that we pretty much get that, so we're going to move on. So how do we name ionic compounds that contain polyatomic ions? Well, basically the same way we named ionic compounds. So when you have an ionic compound, remember you're always going to name the cation and then the anion. If the cation is a metal that can have more than one oxidation state, remember that we're going to use the stock system or the classical naming system to indicate which oxidation state we have here. So let's look at some examples. Let's start with this example here. Here we have zinc, Zn3, parentheses, PO4, 2. So how do I know this is an ionic compound? First of all, it contains a metal. If you contain a metal or ammonium, the cation, the only cation we have that's not a metal, then you know you have an ionic compound. So you're going to name cation, anion. Alright, so what is our cation? Our cation here is zinc. Is zinc a metal that contains can have more than one charge? No, zinc can only have one charge. Its charge is always +2. So we just name zinc. Now what's the anion that we have here? Notice it's PO4. PO4 is part of the 8 series that you need to memorize. This is phosphate. So the name of this compound is the cation, zinc, and phosphate, the anion, zinc phosphate. Alright, let's do NH4, NO3. Okay, so is this an ionic compound? That's the first question you should always ask. The answer here is yes. We don't have a metal, but we realize that NH4 is technically the only polyatomic cation we have, NH4+. The name of that ion is ammonium. We'll write it up here. Ammonium. So the name of our cation is ammonium. Okay, so what is our anion? Our anion follows. It's NO3, but we know that's an anion. That's nitrate. It has a -1 charge. So we name the anion nitrate because that is the identity that you'll need to know for that compound. How do we know? We just memorize. So the name of that compound, ammonium nitrate. Let's do the next one below. PbC2H3O2, 2. C2, sorry, H3O2, 2. Alright, is this ionic compound? Yes, it is. It contains a metal, lead. If you contain a metal or ammonium, you're an ionic compound. So lead is Pb. That's our cation. But one thing we noticed about lead is one of the cations that can have more than one oxidation state. It can either be +2 or +4. So in order to name this compound, according to Roman numerals, we need to, or the stock system naming, we need to put the Roman numerals of whatever charge of the lead we have in this parentheses. So we don't know the charge, but we can figure the charge out. Remember how for the ionic compounds, when we figured the charge out, we reverse the crisscross? You always start with your anion. We always know what our anion charge is. It never changes. So we're going to look at that first. C2H3O2 is acetate. And acetate has a -1 charge. So notice how the subscript for lead isn't shown. It's 1. Does the 1 match the 1 up here when you reverse the crisscross? Yes, it does. Because that number on the subscript balances or matches the number in the superscript up here, we can reverse the crisscross. See the subscript 2 here. We can put a +2 for our cation up here. So this tells us that our lead is a +2 cation. So we have the lead 2 ion. We just said that the name of this ion is acetate, so we have lead 2 acetate. And I totally misspelled that. It's hard to talk and spell at the same time sometimes. Alright, because you're talking one thing, you're writing the other. Acetate. Alright, lead 2 acetate. We had to indicate the charge because we had a metal that could have more than one oxidation state. There's another way to write this. We could also write it using the classic naming system, just as we did before. So remember, the classic naming system uses the Latin base name, plume. And then we're going to add either us for the lesser charge or ic for the greater charge. So this is where you have to know what your charges are for your different metals. Lead can be +2 or +4. Because we have the lesser charge +2, will be plumous acetate. So either of those names is accepted. Okay, so make sure you practice naming and writing the formulas for the compounds. The last thing we're going to look at is something called oxy acids, the naming of oxy acids. What are oxy acids? They're neutral compounds that begin with the element hydrogen, and they end with one of the oxygen-containing polyatomic anions, the oxy anions. So if you have an oxy anion, I don't know, XO, Y, negative Z, I don't know. So like nitrate, sulfate, phosphate, chlorite, perchlorite. If that charge is counterbalanced with a hydrogen ion, which has a +1 charge, then you have an acid. So if hydrogen precedes the oxyanion formula for an overall neutral compound, you have the oxy acid. How are we going to name the acids? What we're going to do is we're going to modify the name of the oxyanion. So, for example, if the name of the acid, or if the name of the polyatomic ion used in the acid ends in 8, you're going to remove the suffix 8 and you're going to add ic acid. You're not going to do anything to the front of the name. So, for example, sulfate, SO4, 2 negative. If we neutralize this with H+, the hydrogen ion, then we're going to need 2 hydrogens to counterbalance the -2 charge. If you come up with the acid of sulfate, you're going to get H2SO4. We're going to take the 8 off of the suffix, and we're going to add ic acid. Now, sulfur is a little bit weird. Instead of being sulfic acid, we use the whole name, sulfuric acid. You've probably heard of that before. Alright, so 8s go to ic acids. Another example, chlorates. Chlorate is ClO3 negative. If you want to neutralize that, you need 1 hydrogen with a +1 charge. So HClO3 is the oxy acid, the acid of the oxygen anion. So we're going to take the 8 suffix from chlorate, and we're going to replace it with ic acid. So chlorate becomes chloric acid. Alright, now the other possible suffix that you can have for the oxyanions is ite. If you end in ite, you're going to change your name to us acid, the suffix. So for example, sulfite is SO3, 2 negative. If you have a hydrogen ion, it has +1. How many hydrogen ions will we need to neutralize the -2 charge? Well, we need 2 of them. So when we neutralize the oxyanion by adding hydrogens to come up with a neutral compound, the compound for sulfite, the acid, is H2SO3. So instead of calling it sulfite, we're going to remove the ite, and we're going to add us acid. Ites go to us acid. So it'll be sulfurous acid. Once again, sulfur, we'll use the whole name. Another example, chlorite, ClO2 negative, 1 less than the 8. When we form the acid, the ite will turn to us acid. So chlorous acid. So let's do some examples. Alright, notice here we have a neutral compound. It starts with hydrogen, but it's got multiple atoms. It's a polyatomic anion acid. This is an oxy acid. C2H3O2 is acetate. This part. But notice that it's neutral with hydrogen. We're going to name it as the acid. Because it ends in 8, we're going to remove the 8 and we're going to add ic acid. So acetate becomes acetic acid. Not too bad, right? Okay. Let's do the next one. H3PO4. We notice we have a neutral compound. We've got hydrogen and phosphate. So phosphate, it's one of those weird ones. The 8 will be lost, and we'll add ic acid. But we're not going to call it phosphic acid. We're going to call it phosphoric acid. It's one of those name kind of stuck around type things, so we use the whole name. Let's do the reverse. So in the next two on the other side, we're going to derive the formula from the name. So here we have the name nitric acid. Remember the ic acid came from the 8. So we're going to start by drawing nitrate. We know nitrate, because hopefully you'll memorize it, is NO3 -1. Sorry about that. NO3 -1. So if we want to make the acid, we're going to use the proton H plus hydrogen ion. How many hydrogen ions do we need? Well, we only need one because we have the negative charge, we have the positive charge. So nitric acid balanced is HNO3. That's all it is. Let's do phosphorous acid. So notice we have the us acid. The us acid came from the ite of the series. So what is phosphite? Well, we know phosphate is PO4 3-. That's phosphate. That's the one I want you to memorize. So ite is one less. So phosphite is PO3 3-. So we know we have a -3 charge. How many hydrogen ions are we going to need to counterbalance that? One for each charge. So we're going to need 3. So when we write the whole formula, remember we don't write the charges in the balance formula, it should be H3PO3 for phosphorous acid. Okay, now we're going to get a lot of practice on a worksheet packet that we're going to do in lab together. But in the meantime, the best way to learn is to practice the rules. Learn the rules, learn the polyatomic ions, learn the metals that have multiple charges. And from there, just practice, practice, practice. That's going to be the key to dominating this chapter.